Beautiful. Morning, Sydney. It's good to see everybody back for day 2. I hope you're all caffeinated, comfortable, all that sort of stuff. As you can see, well, sort of see, because I don't do UX or UI. I'm talking about Bloom filters and code search. I appreciate the irony. I'm very well aware of who is sitting over there who knows all about how to do code search. Don't hate me, man. I did my best, okay? Sorry about the clickbait title. You've got to stand out from the selection process somehow. Why is that not working? There we go. Who am I? I'm not going to bore you with this. You don't care. I'm not famous. You can find me in these places. For those who like half listening to conference talks, everything is up there now, so you can go there and just look at your screen, go off and get coffee, whatever. I'm not going to blame you if you leave. It's fine. Skip the slides ahead if you want. Go for it. Doesn't bother me. So I run searchcode.com, and it's as the imaginative name would suggest, it searches over source code. I've been doing this for sort of 10 years now, whenever Google Code Search shut down, on the behest of Gabriel Weinberg of DuckDuckGo, who said, why don't you do that? And I was like, sure, why not? And I've been rewriting it many, many times. It was originally in PHP, I rewrote it in Python, I ported it to Java, and the most recent iteration is in Go. And it's a really serious side project for me. It's something where I get to have a wonderful time playing with algorithms, data structures, all the sort of cool things that you don't normally get to do in work when you're slinging together HTTP requests. It gets enough traffic to make this interesting, so it gets several million requests hitting it a day, and I get to try things at some sort of level of scale. It's a great testing ground for me to figure out, what happened, do I fail? And I fail a lot while I'm doing it. It indexes about 75 billion lines of code across 40 million projects, and there's been a lot of talk about tests in this conference so far. You'll be happy to know there's almost no tests in it. The internet tests it for me. Thank you very much, internet. But my personal shame is that most of the time I've worked on it, the index was actually supplied by a software project called Sphinx, which has since been forked into one called Manticore. Use Manticore these days. They're both fantastic pieces of software. If they fit into what you need to do, use them. They're absolutely fantastic. But I was abusing them in horrible, horrible, horrible ways. Even the devs are like, this is terrible, don't do what you're doing. And it was causing uptime issues on the site. And searches were taking tens of seconds, and it was causing problems, and people were complaining to me, and I don't want people complaining to me, so I thought, you know what, I'll look at doing my own index. And I felt like a fraud. I'm a search guy, I don't even have my own index, so we're going to solve this problem. Now, of course, the first step with any sort of doing stuff like this is you instantly boast to everybody, this is what I'm doing, I'm this close to success. So, I informed the work Slack channel, I told my friends, and of course I informed my wife, who's contractually obligated to listen to everything I say. She responded with, that's nice. So here's some of the things that go into search and search engines. Now, this is just a small subset. Every single part of those problems you see up there is one of those things you lightly scratch and you discover there's people getting PhDs in it. So I never get bored in this. It's like everything I look at, kick over the stone, wow, this is really deep. And I'm just limiting myself to the index today. I could probably talk about a lot of these for forever, but with, time considerations. So we've decided we're building our own index. Now, we need to consider the goals of search code, okay? Because this influences the design. Now, the first thing is, it's a free service, okay? I don't have to worry about pesky customers. If it goes down, I don't care. I mean, I want to keep it up, but frankly, it's not a big problem if it goes down for a period of time. I want to run it on a single server. Again, I don't really care about the downtime, and it's my time that I'm more interested in, so I don't have redundancy. I try and look after it. It makes maintenance simple. Another thing to consider is Boolean queries. I get asked this occasionally. It turns out most people don't really use them anymore. I don't know why that is, and so I don't need to worry about Boolean queries for it. The code needs to be understandable, so this is where Go is really useful because it is quite understandable. And also, I had rewritten the site in Go, and I thought, well, if I've done that, I've got a single binary, it'd be nice to have the index embedded into it, so I can just deploy this one thing and run it, and great. And the last thing, this is a consideration for you. This is how I built an index, okay? I have no formal training in search engines and whatnot. It's not necessarily how you should build an index. First thing we need to cover, tokenization. So this is where you take text and you break it apart into something you can index. Generally, it's done by splitting on space characters that you find in the text. It gets more complex than that when you're talking about East Asian languages and things like that. It doesn't work for code either. So if you look at the example down the bottom, we've got that I++ in the middle. You should, in theory, be able to search for that and get results for it if you want. And we shouldn't limit people to not being able to do that. So the generally agreed upon solution for searching code is you split it into trigrams. So this is where you break the text apart into characters of 3, and then you index those. Now, there's a few catches with this. One of them is that you tend to get false positives. So there are situations where different inputs will produce the exact same trigrams as output. You also have problems with low cardinality. So if you get like the letter P repeated 20 times, you just get one trigram out of it. It's not really very helpful from a search perspective. The other big problem is that when you tokenize, you get a lot more tokens that you've got to index. And you get these. In this particular case, like I put search code in using split by spaces, I get search code out. If I put search code into trigrams, I get 8 things that I now need to keep track of. And this is an important consideration because it enlarges the index a great deal. So here's some code to generate some trigrams. This is the one that's actually used in search code. The reason I put this up here is this is by far the biggest bottleneck in the indexing process for me. So if somebody wants to profile this and improve the performance, I'd really appreciate it. It dominates the indexing profile by a huge amount. Consider yourself nerd sniped. So what's an index? So this is kind of fuzzy. A lot of people have different definitions of this. For me, it's basically I have a function and I want to pass in terms, and I want to get a list of integers back that say these are the documents that likely contain these terms, possibly ordered by relevance. So textbook 101 example of indexes. So we've got 2 here. So the top one is a positional index. So in Go, it's really simple. It's just a map of string to integers, where the integers are the document IDs. Really, really simple. Okay, so the strings are the terms, integers are document IDs. The document IDs, just in case you're reading literature on this, are usually referred to as a posting list. So if you see posting list, just think it's a slice. Okay. The next example is a positional index. So a positional index is one that stores where the term was found in the document. So in our first example, we can see that Gopher belongs to document 1337. In our positional index, you can see it belongs to that same document, but we found the word Gopher in positions 1, 2, 3, and 99. Now, the problem with positional indexes is when you start indexing like that, you end up with an index that's as big or potentially bigger in the case of trigrams than the stuff that you're actually indexing. Becomes a real pain in the butt. There's another big problem with these lists is that consider a search for the Asvogel, okay? The is a really, really common word. It appears in nearly every document, okay? So the posting list is really long. Asvogel is really, really rare. It only appears in a few of them. So to get documents that match based on those posting lists, we need to get the intersection of the 2 lists. So you do that by walking them, whichever one's shorter, and you just keep walking until you get the situation where the ID is in both. Great, we found a match. And it takes a long time when you get to longer lists. And this only gets worse as you index more documents or you start adding more common terms to search across. So for trigrams, this actually gets quite painful. Now, the solution that's usually proposed to solve this is to implement a data structure that's called a skip list that allows you to skip through the documents the posting list a lot faster. They're not overly complex, but they're sort of like 500 lines if you do it properly, and it's a real pain. For those wondering, an Asvogel is an obsolete Afrikaans word for a South African vulture. So today you learned something. The second problem is memory usage. So posting lists, when you look at them, look like they can be compressed. Compressing them is a good idea because they take a lot of space and memory. The main way that you tend to come across doing this is Shannon Elias-Fano, or sometimes you just see it as Elias-Fano compression. It's a technique that you can use to compress a sorted list of integers. Don't worry, you don't need to understand that. It's not the simplest thing in the world, but it is understandable and you could go and implement. Just assume that it reduces the posting list size. So this leaves us with a lot of complexity. This is a lot more complex than what we started with for our non-positional index. We've gone from a map of integers to we're now needing a map of string to a compressed skip list, which is a data structure that I would have to write. And you need to combine all these things together. So I did, and this is what I got. I basically got 2 turkeys taped together. I did not get an eagle. That's on me, by the way. That's no fault of Go. That's no fault of anybody else. That's purely on me. I'm time constrained. And I looked at this code and I went, okay, let's rethink this. Maybe we can come up with a better solution. What about bit slice signatures? So bit slice signatures, bloom filters, they've got a nice technique to search through. It helps if you know what a bloom filter is to start. So what is a bloom filter? So the technical definition is it's a space-efficient probabilistic data structure. So you add items to it and you can check if they're added, or you can check if it wasn't added. They never return false negatives. So if you haven't added something to it and you check it, it will never say this was added. But they do occasionally give you back false positives. So let's look at this example. This is our bloom filter. It's just 16 booleans in an array. You can think of it as 16 bools in a slice. Really simple. Let's add something to the filter. So we get a term, we hash it multiple times using an integer returning hash like fnv, and then we use the resulting outputs to map to bit positions inside our filter, and then we set them to true. So we've set 3 to it, great. We've now added big. We're going to add another term, same process, 3 bits, set the 3 bits. Another term's added. Now you'll notice here that 2 of the bits overlap. This is an expected property of the bloom filter. This is why they're space efficient. So now we want to check, did we add something to the bloom filter? So we do the exact same process, except in this case, instead of setting bits, we're checking bits. So we check, all 3 of them are set to true, 1 in this particular case. So that means big was probably added to this set. Why probably? Well, that's the false positive thing. We'll get to that in a minute. Another check. This for Sydney. Now you'll notice that the middle bit is set to 0. That means we can be confident Sydney was never added to this bloom filter. And then lastly, we've got an example of a false positive match. So I've hashed Gopher and I've gone and checked the bit positions. We never added Gopher, okay? But 2 of the other terms set those bits. So we would report this as a false positive match. Now, there are ways to deal with this, and you will find that a lot of the tweaking of bloom filters comes down to controlling the false positive match. But we kind of have to deal with that anyway, because as I said, trigrams introduce false positives. So this is not a deal breaker in terms of implementation. So here's a Go bloom filter. It's actually really simple. It's only 4 lines of code, the first 4 lines that you see there. You can actually chuck this in and run it on your machine if you want. It's basically, just as I said, a slice of booleans, a function to hash and set the position. You can see where I've run it there, where I print out what the filter looks like. You can see 2 bits are set. It says something was probably added, something was not added, and a false positive. So really, really simple. So how do we search over a bloom filter? So the trick is you just add more bloom filters. So this is 4 bloom filters, one after the other. And what we do is we hash the terms that we want that have come in at bit positions 1 and at 7. And then we just walk through each bloom filter. We check those bit positions. And if they're all 1, great, it's a match. If any of those positions are 0, it wasn't a match. So in this particular case, document 4 matched, okay? Because both of the positions at 1 and 7 match. Now this is important to pay attention to because this is going to come up in a bit. So bloom filters have got a lot going for them. They're compressed by nature because they're only using a few bits per term. They're also really simple to implement, as you saw. 5 lines of code, pretty simple. Adding to stuff is really simple. So if you want to add onto your search, you just add another bloom filter, you're done. Editing is simple. You just fiddle the bits or you replace the filter. Searching is a simple for loop. It's something that you can hand to your most junior dev or your cousin. You can extend them to counting bloom filters. There are a lot of things that you can do with bloom filters. Of course, there's a problem, so there's no free lunch. So firstly, how much memory do you think 100 million bools takes if you do a slice? The answer is it's almost 100 meg, and if you calculate that out, you're like, hang on, that's about 8x what I expected, and it is. It's because each bit, or the byte, the boolean in this, is actually a byte under the hood. Now this is not a problem with Go. All the languages do this, so. The other problem is that the search is really, really, really slow. And this comes down to how fetching memory out of a machine works. So when you probe a single bit on modern systems, you actually pull back 512 because a whole cache line is read. So this means you've got a 512x overhead every time you're probing a bit. So as a result, you end up walking all of the memory for your bloom filters. So here's an illustration of this. We've got a 2048-bit bloom filter. They're meant to be squares, they don't look like it. We've hashed our term, we matched 6 bit positions, we used a good hash function, so we got a decent distribution, and we probed those bits, and we end up reading all of the memory as a result. So this is not great. And this is a problem because you think, oh, memory access is fast. Modern CPUs, yeah, they can push sort of like hundreds of gigs across the CPU per second. But you know, that's in theory. In theory and practice are the same. In practice, they're not. You're probably more likely to get 50 gig per second. So if your index is 100 gig in size, you're limited to one search every 2 seconds. Surely we can do better than that. So in 2017 at SIG-IR, this paper about bit funnel was released, and basically it details how Bing flipped to using bit signatures for their fresh index. And it won the best paper at SIG-IR. It's probably one of the most prestigious IR conferences. And the thing that really got my attention is that Dan Liu is a co-author. Anything he writes I pay attention to. I have a personal model, good enough for Dan Liu, good enough for you. So this is one of the fixes that was discovered in the 80s, actually. So a smart guy called Roberts noticed you could rotate the bloom filter. So assuming the filter has all the same size, in this case they're all 8, we do that by turning the rows into columns. So each row used to represent a document, but now each column does. And remember, it's filled right to left. So document 1 is on the right-hand side, up to document 4 on the left. So with this done, now we only need to inspect the row positions for our query. So we were looking at 1 and 7, so we extract those out, 1 and 7, and then we logically AND them together, and we keep the result. Now the nice thing is that an AND in a CPU is basically free from a computation point of view. It's so fast you don't even have to think about it. And this means that basically all of the time is spent in just about memory lookups. The other thing you'll notice as well about this is we're now searching 4 documents at once. So we've got a 4x speed increase just from that alone. In this particular case, the leftmost bit is still set after our logical AND, which corresponds to document 4. So we got the same result, but we did a lot less and we did it in far fewer operations. Now, the result of this is it reduces memory access by a huge factor, particularly across larger bloom filters. I've seen estimates of something like 200 times less memory access. Great, so we're off to a flying start. So the next step is to continue to save space. So what this code does is it packs the bloom filters into a big slice of int64. So we've got a whole bunch of int64s, of the size of the bloom filter that we've got. So I think in this case, it's 16. So we've got 16, and then we start filling right to left. So we add a document into it, which is fairly simple. We get the document, we turn it into trigrams, we hash it into the normal bloom filter, we pass it into this, and it fills up the bits right to left. Very simple from a code perspective. This is something I understand. This is what it looks like after we've added 32 documents. So you'll see half of it, the bits are set, all of the rightmost bits, all of the leftmost bits are not being set. So hence they're all 0. And that means we can add another 32 documents to this. And you're probably going, what happens when we need to, add document 65? Well, we just add another 16 bits, 16 ints, and then we start filling right to left again. Now, the good thing about this is we're optimally using the space. We were previously using a byte to store a bit, we're now using an individual bit. So this is fantastic. There's no 8x overhead. It also becomes really fast to iterate this in code because it's just a slice of ints, so it doesn't get much faster than that. And when we do a search operation on this one, all of a sudden we're now searching 64 documents for every AND operation, which is a huge speed up. There's still a fair bit of waste in this approach though, because it turns out smaller documents don't need larger bloom filters. So what we do inside search code is we shard based on the document length. So bigger documents go into bigger bloom filters, smaller go into small ones. So what happens is when the document's being indexed, it determines the number of unique trigrams and then it picks an appropriate size bloom filter to achieve an appropriate bit density. So I think I aim for about a 30% bit density across the bloom filter. And this is done to avoid overfilling the filters, which means that every test that you do against it says, yes, this thing absolutely exists, or underfilling them, in which case we're wasting space. Shards have different sizes. I think I shard about 16 ways in search code. It kind of changes on its own. This is sort of logically how it looks. So we've got the index, which consists of the various shards of different bloom filters, and then we have blocks inside those. Blocks are just 64 documents appended to that one slice. So when you're working with really large slices and you're constantly appending to them, which search code does, particularly when it's indexing, you get a great deal of value by copying the slice into a fully allocated one up front. It stops you from having memory fragmentation. In our particular case, it gives a faster search. And it means we're using the exact amount of space that we need to store our filters. So in Bitfunnel, one of the things they implemented was a thing called frequency conscious bloom filters. Now, the reason for this is that terms like the appear in almost every document, as we talked about. So you can get away with false positive matches on it, because if you falsely match a document that's got the, well, I mean, it probably did anyway, and if it didn't, it's a real outlier. It's not a huge problem. It does mean, though, however, that when you match on usvogel, that is a problem, because if you're falsely matching in every document, it doesn't exist in every document. So basically the result is that you use more hashes on the rare terms to drive the false positive rate down. Okay, don't overthink it. Just think rare terms, hash more. This is an early prototype function I had for this. It's fairly horribly written. I iterated on this code more than I care to admit. The result for that was basically a lot of wasted time. So what I ended up doing at some point of staring at this code for days on end was I tried testing fixed hash counts. So basically what I said is, okay, let's throw away the frequency stuff. Let's just assume we do one hash and then we'll do two. And I tried this up to 10, and then I tested that against the frequency conscious ones, looking for what result gave me the lowest false positive after indexing. I think I did a couple of million lines of code. In almost every single case, 2 hashes worked out to be the best possible solution to give the best noise, signal to noise ratio. Yeah, the new algorithm, it's really mind-blowing. I'm really proud of that one. I suspect this is probably due to trigrams not being as unique as you think they are. They're probably fairly common across a lot of code, and none of them really stand out as being a true outlier, unlike natural language. This one probably seems counterintuitive. So the thing is when you're working with processes that are pushing your system limits, doing things in serial to an extent kind of feels faster for users. So imagine a query takes 1 second, okay? Every time we want to do a query, 1 second. So if 10 users come in at the same time and we start processing them all, they all get the answer 10 seconds later, more or less. If you do that in serial, the first user gets it in 1 second, then the next gets it in 2, and then 3, 4, 5, 6, 7, 8, 9, 10. Way better user experience. And this is where I really, really, really like Go. So this is a counting semaphore to limit concurrency to a function. I remember writing one of these in C#, I think it was, horrible, and it was the most horrible bug-written thing I think I've ever done. To just have something so simple in Go like this just speaks to amazing language design. It really shows how flexible it can be. So this is the core search loop. Personal anecdote, I find this algorithm beautifully simple. And when I say the core search loop, I mean this is the core search loop from SearchGo. So what it does is it takes in query positions for the search. So in the case of searching for search code, we've turned that into trigrams, and then we've hashed them twice. So we get 16 integers from 0 to 2048, because this is a 2048-bit bloom filter. We then walk over each logical block of 2048 integers, and then we logically AND each row that we're looking at. And if we see all zeros, because A, there was nothing that had these things matched, or we've ANDed them together, we had zeros, we bail out. So you'll see that important skip shard of nothing. That's really important. This is why this thing goes fast. Because if you ever hit that, you are potentially skipping 16 kilobytes. 16 kilobytes? Yeah, 16K of memory that you just instantly skip over. This is what keeps it quick. You want to hit that case as often as possible, because that's what keeps the search running really fast. And the other reason this is really fast is it's basically just a for loop. You know, we all know for loops go burr. The other thing that we're doing here is at the end, when we do have a match, we walk all of the bit positions within the integer that we were found. We know where that integer sits in terms of the slice, and we can say this is the document ID that corresponds to it. Don't overthink it. I do have a copy of all of this if you want to look through it later. I'll give you the link later. Yeah, you know, for loops really do go brr. So visually, it looks like this. So this represents that bloom filter, and you can see where we're going through and looking at all of the individual rows and then ANDing them. So from a memory perspective, this is what you get. This is actually something I would really like to turn into a visual dashboard on the site at some point, just so I can see how the searches look. And you can see occasionally, you know, it hits some condition where it goes, great, we got zeros, just bail out, jump to the next one. Now the final result of all this. So I managed to bring the index search time down to 50 milliseconds, okay? Considering the tens of seconds I was previously getting, I was pretty happy with this. It was a massive, massive, massive improvement to the service. This is generally searching 140 to 180 million documents at any one time. This changes depending on what's going on in the system, simply because it's doing things like duplicate code detection, removing the duplicates, it's checking for minified files, it's checking for binary files in order to remove those. So it's constantly changed. The index aims to be at 100 gigabytes in size. I'm looking to see if I can come up with ways to reduce the size a bit further. If you do go to searchcode.com, if you do search for something and you're curious about this, just view the source and you can see that thing in the bottom. It's just a nice div that gives you what's going on. It's not as fast as the times reported by the Bing Bitfunnel guys, but I mean, they had a few advantages. They've got Dan Liu for a start. They were using highly optimized C++. They don't have to deal with trigrams. They did some additional tricks, which I suggest going and having a look at the paper because it's actually quite cool what they do. They do a thing called higher ranked rows, and also they actually know what they're doing. So a few conclusions. I doubt I could have done this in another language. Now, I like Go. I don't love it. It doesn't push the happy parts of my brain the way that Python does, for example. But it gets out of the way, and while I want to hurt myself every time I write a nil check, I realize, hang on, but I've already solved the problem. I solved it really quickly. The solution's solid and understandable. It works pretty quickly, and I just kind of move on and forget about it. So yes, it doesn't push the happy parts, but I mean, maybe that's the advantage of it. It's not meant to, it's just meant to. You solve the problem and move on with your life. So absolute success there if that's the design goal, which I think it is. The other one that I've really got is that bloom filters and trigrams work really well. I asked ChatGPT about this, because why wouldn't you ask ChatGPT about this? And it said it was a stupid idea. You should never attempt this, it won't work. So sucks to you, ChatGPT. As far as I know, this is a globally unique approach. Nobody I know is doing this. And I know search engines tend to be fairly cagey about what they're doing. They don't discuss these sort of things, so it's possible. But nobody appears to have married these two together, so I'm claiming global uniqueness on this. I've actually uploaded a minimal version for you there. As I said, everything's linked from boyter.org. It has pretty much everything you saw. It will give you enough to actually try this sort of thing and play around with it. Now, of course, the users using search code probably don't really care very much that it's running on some sort of a unique bloom filter trigram backed index with borrowed ideas from Bing. But I know, and now you do too. Thank you very much.